Greetings, everybody. Welcome to Organic Chemistry 1. Now you see where my headphones rest after videos. We're going to get back to chapter 9 right now. And we're going to review what we know already about substitution reactions. And I'm looking for my pen here. Yeah, I found it. And it's all about carbons with leaving groups. That's how we start this chapter. So let's look at what a leaving group is. And a leaving group is a species that's stable when it takes its electrons and leaves. Okay, so generally they're anions, but they do not have to be anions. We have a good system for classifying leaving groups based on pKa's of acids. All right, so the leaving groups are the conjugate bases of strong acids. pKa is less than 0. What category of leaving group is that? It's an excellent leaving group. If you have, I'll give you a quick example of an excellent leaving group right here. How about examples up here? I minus. I minus is the conjugate base of HI, hydroiodic acid, pKa -5. All right, how about an acetate ion? So OAC is a nice short form for acetate ion. It's the conjugate base of acetic acid, pKa of 5. It's the conjugate base of an acid between pKa 0 and 12. 5 is between 0 and 12. We have a good leaving group. In our chapter 9, we're only going to focus on excellent leaving groups, okay? But later on, we're going to see lots of examples of different leaving groups, and poor leaving groups generally mean you should not be talking about a substitution reaction. You have to have at least a good leaving group. So think of a poor leaving group. My favorite is hydroxide. You will not see hydroxide leave in a substitution reaction. It's a poor leaving group. It's the conjugate base of water with a pKa of 16, which is definitely greater than 12. All right, so just trying to tie it into chapter 4. When we had H attached to an excellent leaving group, we just called them a strong acid. We didn't say anything about leaving groups at the time. Well, now we can say we have 7 excellent leaving groups because we knew 7 strong acids, 3 of them here. Perchloric acid is not here, but it's on our table in chapter 4. Nitric acid, it's also strong acid, and toluene sulfonic acid, TSOH. Means their conjugate bases are all excellent leaving groups, so we should be ready on tests to draw complete Lewis structures, maybe Lewis, for all excellent leaving groups. So look at this exercise. Draw the Lewis structure for the leaving group in the molecule above. This is the perchlorate ion. Perchlorate is very stable. It has extensive resonance. And chlorine is highly oxidized too, which makes perchlorates dangerous in a different way. With that high oxidation state, they're found a lot in explosives. But perchlorate as an anion is very stable. You can draw 3 other resonance forms equally stable to this. So there's your answer to A. And what is the name of its conjugate acid? Well, B, HClO4. I don't want to impinge on the next area here. B, HClO4 is perchloric acid. And ic acids, as their conjugate bases, have 8 ions. In this case, it's the perchlorate ion. Answer C, right underneath the ion perchlorate. There we go. And what else are we supposed to do up there? Nothing. In D, we're supposed to identify the electrophilic carbon, the one that will be attacked by a nucleophile. And that's based strictly on partial charges. If you have a carbon with a bond to oxygen, that makes the carbon slightly positive, which is very attractive to nucleophiles. Nucleophiles are seeking out positive. That's what their name says, nucleophile. Love that nucleus. Why? Because it has positive. Okay, so we identified the electrophilic carbon. Not really, we didn't. Electrophilic carbon right there. Show the mechanism for an SN2. Well, that's the one, SN2. You're going to program your mind always. As soon as you hear anybody else say SN2 or you read SN2, two words come into your mind: backside attack. Okay? When you hear the words SN1, one word comes into your mind: carbocation. In fact, if there's a 1 in the name at all, you should say carbocation. Just mindlessly, just say it. It'll help it stick. SN2 is about the backside attack. Remember, the 2 means 2 molecules must meet, and the backside attack is how they meet. How I Met Your Nucleophile. Coming soon to a TV screen. All right, so nucleophile backside attack. What happens to your stereocenter? This is important. We need to constantly review what happens to a stereocenter in both SN1 and SN2. Remember, we just said it's a backside attack. You're breaking this bond, so you need to know what the backside of that bond is. Well, what's 180 degrees from a wedge? A dash. And your nucleophile is going to be on that dash. And the H gets pushed out by the backside attack. And your stereocenter used to be R. This is bonus. It wasn't asked for here, but it used to be R. And I'm assuming your nucleophile has a higher priority than carbon. I think they all do. So this would have to be S. Yes, SN2, stereochemical outcome. Review last day's lecture at the end. Stereochemical outcomes of SN2 are stereochemical inversion. That's to say R becomes S. Now, that's the SN2 attack, part E. Part F, SN1, carbocation. See, I got myself going. First step is make a carbocation. Leaving groups do what leaving groups do. They leave. In both examples, they must leave. In this example, we're generating a carbocation. And if you want to draw wedges and dashes, I don't know why you would want to, because this thing is now sp2, trigonal planar, flat. And how are we going to show on the test that we know this? That sp2, there is no backside anymore. So you're either attacking from the front or the back. Oh, I just want the arrow. There we go. This is the RDS. If I wrote that down, would you know what it means? Yes, making a octet violation is always going to be slow, rate determining step. Half the time the nucleophile is going to come in from the front. So that would be on a wedge. And that necessitates the H being on a dash. And the other half the time, it's going to come in from behind and kick the H out front. And we've got nucleophile on a dash. And that's a RS mixture, 50-50. We have a word for that, racemic mixture. So what's the stereochemical consequence of an SN1 reaction? Racemization. Make a racemic mixture of 2 enantiomers. That's kind of redundant to say it that way. That's what a racemic mixture is. The 50-50 mixture of 2 enantiomers. All right, well, we're looking back a little bit here, and you're probably just a hair confused, saying, okay, doesn't this molecule know what it wants to do? It's doing SN2 here. It looks like the same molecule to me. And the SN1, well, why does it sometimes do this and sometimes do that? Please try to remember that the barrier for SN2 and SN1 on a secondary carbon is, which is what we have here, secondary RX. Shouldn't put that in green, let's put it in black. The barrier for SN1 and SN2 was very similar energy. Look at those energy diagrams. So you are going to get a mixture of the two reactions. As a good chemist, you want to be able to control which of the two can happen. And that brings us to how we can manipulate reactions using other factors other than Rx. And we hinted at this the other day. The players we need to know in the game are Rx. And I'll do a quick review on Rx. Tertiary could only do SN1 because it could only do carbocations. And primary and methyl could only do SN2 because they can't make cations. And secondary is where we had some wiggle room because there was competition. So if you choose an appropriate nucleophile, you can favor one reaction over the other. And if you use a strong nucleophile, the important thing is those things enhance the rate of the SN2 reaction when you use a very strong nucleophile. Do you see something that all the very strong nucleophiles have in common? Just take a second. You can glance down here and compare it to the next category. None of these have something that all of these have, and it's called a minus charge. So you're saying, okay, this is a lot of stuff to memorize here. I want to keep the memorizing to a minimum. So all the very strong nucleophiles have they're an anion. Okay. Very strong. Strong. Must be anionic. There's one exception here. And we even talk about it down here. All of the strong nucleophiles have a net anionic charge, but one of the nucleophiles is an anion without being a strong nucleophile, and it's right here. Carboxylate ion doesn't belong up here because it's doing this. Carboxylates are resonating, and this is the best resonance. 2 equal resonance forms. Not that interested in attacking stuff when it's stabilizing its minus charge like that. So just keep in mind, don't put carboxylates up here just because you see the minus charge. They belong down here. And what is a carboxylate? It is the conjugate base. Base of carboxylic acid. That's how it got its name. Okay. Let's see. There's a lot of things here that we could condense down to one structure. HS and RS minus. Just remember RS minus. R equals C or H. Makes two things into one. Hydroxide, alkoxide, same story. RO minus. R equals C or H. Just make sure this is not a carbonyl, right? If the carbon attached is a carbonyl, what do you have? We just talked about it. We have a carboxylate. Don't put it up here. So normal carbon groups. So that makes that a little easier. Cyanide, acetylide. That's our old friend from chapter 7. Yeah, they look very similar. It's got a C triple bond to N or C. It's going to be a great nucleophile. And the nice thing about those two is they're very easy to make, as we learned in chapter 7. Take the H off of a terminal alkyne and you make that. Iodide and bromide are here. Chloride is not, and it doesn't really belong here. Chloride, with its high electronegativity, doesn't like giving up its pair of electrons in backside attacks as much as these two. I put chloride down in the moderate category, but I don't want to confuse the statement, so I'm not even going to use it. I won't use chloride as a nucleophile. How's that? What about these three things? They're all sulfur, just like up here. But, you know, sulfur without a minus charge is not as attracted to a nucleus that has plus charge as a sulfur with a minus charge is attracted to a nucleus. So, yeah, that makes sense. Neutral's not as attractive to positive nuclei. And let's do moderate and light green. Moderate nucleophiles don't speed up or slow down SN2, so there's kind of like a weighting pattern here. They don't favor one reaction or the other. This is really, all three of these are one thing. Just call them R2, R, condense it down to one thing. I make it green too. RSR. How about RSR prime? R prime, C or H. That's one thing now. I just call this the neutral sulfur nucleophile. Up here, I call this the anionic sulfur nucleophile, and that covers everything. Don't make it three things. It's one thing. This is one thing down here, a neutral nitrogen nucleophile. Make that one thing down here. Well, R bonded to N, bonded to R prime, bonded to R double prime. Lone pair. Do we need the lone pair? Yeah, that's the nucleophile. You don't need it. Oh, wow. Harsh. Don't really need it right now. I mean, when you're doing the mechanism, you need it. Good enough. R prime, R double prime. C or H. It's the one category. It covers a lot of things. And this covers a lot of things too. RCO2 minus, RCO2 minus. That could be an H out there. It doesn't change anything. And then that's the moderate category and the poor category. Very similar. Poor, slow down SN2 reactions. Okay. There's only one thing down here. R, O, R prime. R prime equals C or H. It's the neutral oxygen category. And so there's a lot less items on here than it might first appear. Just make sure we're separating things out here. And here. Yeah. Oh, that's tricky. Yeah, I told you. And because this is in the moderate category, isn't it? That's not going to straighten it out for me. I'll live with it. Okay, we haven't saved in a while. So we have to know our nucleophiles on the test. And it's not just for this test, it's for every test. We're still talking about nucleophiles all the way through Chem242. Just ask my students right now. Got to know these nucleophiles. You're not learning them for just this test. And that's one factor. So how do you speed up an SN2 reaction? You use the top nucleophiles. They make SN2 reactions go really well. Oh, that's not what I thought I had. Thought I had this. SN2. Bottom category, just look carefully at this. They slow down an SN2 reaction. If you want a nice picture in the textbook, look at the textbook, how they actually stabilize cations. If you're stabilizing cations, you're making them less reactive. Oh, sorry, you're making them easier to make. Okay. Sorry, misspoke there. Stabilizing cations speed up SN1 reactions. Nucleophiles slow down SN. I'm confused. I got solvents in my brain because they're next. I was talking about these as solvents. Yes, there's a lot of crossover too in these. You'll see some solvents that are nucleophiles. You'll see some nucleophiles that are also leaving groups. Don't try to make connections that aren't there. I will start over with what I was just trying to say before we finish our first segment here. As nucleophiles, these things do not like making a new bond. If any of them makes a new bond, they become this. They're making a bond to a new thing. Just call it, I don't know, R double prime. And that thing has a plus charge. You're talking about the second most electronegative element on the periodic table now having a plus charge. These are never stable. They do not like becoming these things. They slow down SN2 reactions because they don't want to do this. So get rid of it. They just don't like it. Okay. And I think I just changed my mind. I want to get through the solvents. And that just makes the segment a little longer, but not terribly. Notice we have 3 categories of nucleophiles: very strong, moderate, and poor. We also have 3 categories of solvents. And they're in pink and yellow and blue here. And all of these up here are polar protic. This is when I started speaking by mistake on the previous page. They all stabilize carbocations. And I'll just do a quick diagram here for you with methanol. Methanol's got lone pairs and a very tiny hydrogen. So if there's a carbocation nearby, that lone pair can get quite close to the C without attacking it. Just get close to it. And we, all the oxygens can do that. And I'm kind of stealing this from the book because I said some confusing things a second ago. And they belong here. They weren't confusing in this context. And, you can just keep doing that. The oxygen lone pair gets close to the cation and makes it easier to make the cation. What reaction is going to speed up if you can make the carbocation more stable? Well, how about the reaction that makes a carbocation? Which one's that? SN1 or SN2? SN1 carbocation. See, got myself programmed. So you are speeding up SN1 reactions by choosing these. And I don't look at these as 4 things. These are one thing, one. And this is for the students who pay attention to all their chemistry classes. These are hydrogen bonding solvents. H bonded to O in a molecule, H bonded to N in a molecule makes these molecules all candidates for hydrogen bonding. Those are the ones that are called polar protic. It's not 4 things, it's one thing, including millions of molecules, right? Because we have all these variables out here, R's. So hydrogen bonding stabilizes, that's not what stabilizes the carbocation. That's what helps us memorize what fits in this category. What stabilizes the carbocations is the O, or we could have used this N, getting close to the cation. Polar aprotic solvents, why are they polar? Well, these are clearly polar because they have O bonded to H or N bonded to H. This has C bonded to O. What's the difference in the electronegativities between those? 3.5, 2.5, difference of 1.0, making that, yes, our classic polar covalent bond. Polar covalent bond. Now, is hydrogen involved in the polar covalent bond? Answer, no. If hydrogen was involved in the polar covalent bond to O or N, we call that polar protic, talking SN1. No hydrogen here or here. These hydrogens are not polar, they're bonded to carbon. So we have polar covalent bonds everywhere. Well, in all of the molecules, not everywhere. And the cation right there for sulfur, right there for carbon, and right there for this carbon. Anion for nitrogen, partial anion for oxygen, all because of electronegativity, right? And there we go. And these solvents speed up SN2 reactions. You want a diagram for that? I'll never ask you for the diagram, but the diagram in the text will show you the way these can stabilize the transition state of an SN2 reaction. And you remember, if you have a potential energy diagram and you're doing an SN2, and if you can stabilize what's up here, then stabilize that, it goes to this. Sorry, the color changed. Oh, want to be more obvious than that. You brought its potential energy down. You didn't change the start and the end potential energies, but now your EA is smaller. What's EA stand for again? Activation energy. Why is it backwards? Blame the French. It's energy d'activation. We go backwards. Activation energy. And this one's faster. Why? Because the transition state's more stable. Why? Because you put an SN2 solvent in the polar aprotic category in the mixture to help speed up the SN2 reaction. Good. Add polar aprotic solvent. These are SN2 diagrams. Backside attack, leaving group leaves. Non-polar solvents, they don't help any reaction. But what they do is they provide an environment that's very unfriendly for cations. I know this has lone pairs like this oxygen, but because it has two ethyl groups, it can't get the oxygen close to the cation. And yeah, none of these are destabilized cations. So what's going to happen to that reaction that involves cations? It slows down. What reaction is going to take over? The other one, SN2, backside attack. So they're cheap molecules. That's why we like to use them. They don't speed things up, though. They just stop the SN1 reaction happening to make SN2 happen. So for the rest of today, we're gonna do analyses of reactions. I'll give you a preview of where we're starting after the break. And these are all problems from the book. Practice problem 1, practice problem 2 here. And you'll notice on these notes, I've copy pasted them twice so you can have the blank on top, and then we'll do the answers down here, and they won't even be upside down. In the book, they're upside down. And we'll do that for a while, and we'll learn about 2 new reaction types before the day's over. Those don't begin with SN, they begin with E, and E stands for elimination, but we're going to focus on substitution for at least the next segment and probably most of the third segment. So I'll see you when I see you for those.